what we're going to do is to further analyze the data and try to understand the limits and the values we are dealing with, as well as how these values are related to each other. This is what we are going to do in this lecture and the next lecture. So the first thing we need to understand is we have first to we want to look into our results. The most important result we have is RUL, which is remaining useful life. So in order to understand how this result, we simply want to make a histogram of this result, and we'll explain what is a histogram and why we do it. So first we have our distribution plot in Seaborn library. Of course, SNS is Seaborn library, and dist plot, and we take this data. Of course, in our case, we only have one column, so we just put it. So what we can see here is the remaining useful life and the density of these results. And as you can see here, we have between like 0 to 20, like many, like about 25 is you have a high values of remaining useful life. Still big amount of values has 50 to 100, and more than 100 we still have a peak here and a peak here, and other values also exist in here. So we of course this graph is just try to kind of interpolate these values to put it into a graph. However, what we mainly care about in the histogram is this one, or a density, or in this we call distribution plot, which is actually more or less a histogram. However, we will build histograms for the later data, but for now is this is in one line, we can have all these datas, and we can understand that most of data we have exist here and here. This axis is going to be the amount, the data value, and this here, these numbers, or this shape shows you where these numbers are concentrated. So this is the first one, and after this one, we need to also go to the test data, and we want to just have a summary about its results. So here we have this is just the data frame, and this is one of the pandas features, the data frame dot describe. And you can see here we have a 100 values with 100 engines. The mean of these values is 75. We can also show it in this way. Yep, no, here is only one value. So the count is 100, the mean is 75, the standard deviation is 41.7, and minimum and so on. So let's go one by one. So the first one is the count of the value is 100, is basically what I said, like we have 100 engines. The mean is 75.52, means it's the average. Actually, it's kind of the average, in which if we have values like 1 plus 2 plus 3, we will have 6, and the mean of these elements, or if we have elements of 1, 2 and 3, the mean of these elements is going to be well 6. You sum them, over, so the summation of these elements over their numbers, which is 3. So the summation is 6 over 3, the average is 2. So this is going to be, the mean in our case is 75.5. Standard deviation is a little bit well, a little bit different, but it shows us how these values are spread around the mean value. So standard deviation will equal basically the square root, so we can say to the power of 0.5. So this means, as you know, like the power of 0.5 is equals to the square root. So this one is can be used as a square root, and we take all the elements and x mean, and this has to be squared. So and divided by n minus 1. So this is the equation of the standard deviation, in which we have this value. We have the elements minus the mean. We take every element minus the mean, and we square root of it and divide by n minus 1. All of this has to be summed, so the summation of all of these elements, and then we take the square root of this value. Usually what we have to understand that when we change the data, or if you have two data sets and you want to know which data is more spread around, the one with the higher standard deviation is more spread. So it shows how the data is spread, and this is sometimes we actually use the standard deviation value to consider if the value is very far, like consider it as an outlier. Usually they say 3 standard deviations. So we calculate the standard deviation, and if the value is 3 standard deviation more than the mean value, we consider it as outlier. It's sometimes like this, we can consider it. So you can of course search more about the standard deviation, but in general it's just an equation that shows how the data is spread when you have the normal distribution. Of course you can I can print it in which that if we have a line like this and this, and the distribution can be for example this way. So this is going to be like the standard deviation, a value, and if the value of the next standard deviation is less than this one, the curve will look more narrow. So it's in general it's that's it. Like you don't have to care much about it. Okay. Now, on the other hand, so this is the first one. Now we go for seeing the other values. So data frame train dot describe Of course, here we have many values. You can just write it like this, like you can put the variables here, or you can just flip it. If you write .t, it will write the values here. So for me, I think here is easier to read, so I just put it like this, but it's up to you. You can just write or show it the way you want. So here you can see the other values. Of course, count, mean, standard deviation. Minimum is the minimum value. 25 percentiles, 50 percentiles, and 75 percentile, and then the max. I didn't like explain this one, the 70, 25, 50, and 75 percentile. The idea is here is if you have like these engine values, the maximum value is 100, as we all know. The minimum value is 1. Now 25 percentile, that means this value 26, 25% of these values are less than 26. And 50 percentile means like 52% of this value, or 50% of the data of this value is less than this value. 75 percentile means 75% of the data is less than the 75 percentile. And you go through the other numbers. Here is very nice because it's from 1 to 100. You can really imagine how much these values are. So this one is the train, and we can look into the test also. So here you can test, and again these values can appear. Of course, the main use of these values is just you look into the you investigate, you see these values. Is there like abnormal values or not? This is very important. So this is a summary, and after that what we will do is we diff and train dot. This is also a nice feature of pandas, histogram, and pens. Pens is just how many pens we want to use. Of course, more will have a better, more accurate result, like the representation, the graph. So here we want to, the train data, we want to see the histogram of the train data. Sorry, I didn't put here equal, and actually we have to show the dot show. So now we will see is these histograms, and I prefer this representation rather than the one before, like the density, like kind of statistical entity. I prefer it this way because you can see the actual number. So the values in here, we can see also the histogram. However, now the representation will be simpler. That is, these are the temperature range, and this is the count. So you can see the cycles, for example, with time in cycle, like how the values, and most of the cycles is say in this value. Setting 1, setting 2, these we don't know what do they mean. For example, if we go to the temperature, you can find that most of the time the total temperature of the LPC outlet is about 62.5. So you can see here we have most of the number, which is 1000 in here. Of course, this is drawn with 50 counts. If you want more like just more smooth representation, but it's taking a bit more time, so you can just increase it and you can have a smoother curves, but 50 is good enough. So here you can see what is the range of your values, where and how much of these values exist in every category. So this is a very interesting and very good representation of our data. Now, of course, we have to make the same thing, but this time we're gonna do it for the test data. And in a good way, like we should have similar graphs. In a bad data, the test data is very different. But however, as I said before, like usually what happens is we will have data and then we split the data. This is what we do in as a general practice. Of course, yeah, you can you can split it by yourself, or you can actually um, split it by like a software, um, or like randomly, or you can actually just take like the last 20 or something from the engines, but usually everything is done randomly. Now for here, what we will see in these datas is that we have some values here, this, and this 1, 2, 3, 4, 5, 6, 7. I think it's a little bit not very easy to see. Let me just put it 50. These are the datas in which they have a constant value, and constant value is not a good thing. That is, we if it's not going to change, then it's not gonna give us an indication of what is going to be the life of engine or anything. So what we will do is we will remove these constant values. To do so, first we need to make a variable values, and here we have to be careful. So we have to go one by one, basically. So setting 3, pressure. So here you can see setting 3, and total temperature fan inlet. In order not to make ourselves error, we just take this one, or column names, we can print it out. We can just add or insert. Of course, you can also write the like there is another way to get it, but let's say we have already the values in here. So we go for we say setting 3. So we take setting 3, all this variable, or the name of the column. This is a constant to total temperature fan inlet. Total temperature fan inlet, this one also. It's also beneficial actually to include the unit, but we didn't do that. But it's not a bad idea. Pressure fan inlet, pressure fan inlet, and a total pressure bypass duct. Total pressure bypass duct. Total pressure bypass duct. Engine pressure ratio. Engine pressure ratio, this one. We have burner fuel air ratio. Burner fuel air ratio. Damped fan speed and damped corrected speed. Damped fan speed. and damped corrected fan speed. Yeah, this one we don't need it anymore. Just remove it. Can add more of these. So yeah, this is the the list that has these the values that we want to remove. So what we will do now, we will drop these from the df train and df test dot drop, and drop means we drop the whole column, and we pass it through this function. The axis is of course column in place equals true. And now we already dropped it. You can see the values in here. We used in place because well, basically this statement can be written in this way. Well, dtrain equals dtrain and this one. So basically drop these columns and save them here. So this is why we put drop equals true. Another important thing for us to do is to check if we have NA values or not. So for that, we have to check these our training and testing data. Features equals list df train dot columns, and for feature in features we need to count them. So here what we did, or just let's finish the syntax to count them. Feature here going to be the name of the column. Syntax. Of course, this is in A. Is it in A or not? Basically, this one here, finish, and just run it and see how it goes. Feature, correct. This one. Yeah. So what we did is first we took the names of the data frame, dftrain.columns. It will take these data frame names and will assign them or put them into features. There's going to be list. of like of the columns names. You can see here list of the columns names. And for features in features, print feature, it will print this name, and of course write this and then string, and just count, go through the data frame train and see if it has NA values. Of course we can do this one, and we can just copy paste it and do it for the test as well, and run it, and we can see 00 means there is no NA values in our data.